forgot to check. Is it Friday?
I think it's
Wednesday?
Six.
All right.
Yeah, it's Wednesday.
Okay. So, exam 3 is Wednesday. Oh, thank you. Yeah. You're just going to have to listen more carefully. Exam 3 is Wednesday, the 6th. And the topics are everything up through linkages. So there's not going to be any of this new rotating coordinate system stuff. And, okay, so no rotating coordinate systems. And so today, or Friday, or Monday, I'd be happy to answer questions as they come up about linkages. But outside of that, we're just going to move on to the new stuff. Yeah?
We found this on the homework that I think you had a mistake on.
Okay. In the solution or the problem?
The solution.
Yeah, okay.
If you don't mind saying it. And it was Wednesday the 23rd, and you had a solution. You found the moment, and then you used what the number you found for the moment for the angular acceleration.
Oh, instead of solving for the angular acceleration.
Yeah. Well, you wrote down at the top angular acceleration.
Oh, but then I just used the wrong number.
And used the moment, so I didn't know if that was like.
Yeah, that sounds just like a dumb little mistake. So, what number was that?
That was number 2.
Okay. All right. Yeah. Maybe I won't look back at that, but I'll try to remember to. But yeah, it sounds like right. You got to use the angular acceleration, not the moment, for that. Okay. So I wanted to go through the quiz. Let me hand out a couple of other ones. Okay, so in the quiz, you have two bodies. This one has a length of 0.2 meters, and this one has a length of 0.1 meters. This angle's 45. And the question says, when you're done with Newton's laws, so after Newton's laws, you have 4 equations. Those come from the moment equation for, if I call this body 1 and this body 2, the moment equation for body 1, and then Newton's second law and the moment equation for body 2. And the variables, there are 6 of them. And those are F12, that's a full vector. The acceleration of 2. And what does that one mean? That's sort of shorthand for something, but what's that the acceleration of? Yeah, that's the acceleration of the center of mass of body 2. That needs to be in there because there's no fixed point for body 2. And so Newton's second law involves the acceleration of the center of mass of the body. Okay? So anytime there's no fixed point, you have to have a variable that's the acceleration of the center of mass. And then alpha 1, and alpha 2. And the question is, what are the constraint equations? Well, first we need to know how many we need. How many constraint equations do we need? Yeah. So we need 2 constraint equations. And those are going to come from saying that according to member 1, the acceleration at, let's call this B. So the acceleration of B, according to member 1, has to be equal to the acceleration of B according to member 2. So according to member 1, this one has a fixed point. So we don't need to use relative motion for this one. We can just use the watermelon equation. So the acceleration of B is equal to the angular acceleration of the body crossed with an r vector, and we'll talk about that in a second, plus omega of 1 cross the quantity omega of 1 cross r1. I think this says there's no angular velocity for member 1. And so this goes away. And now what's the r vector? What's r1? Describe what that is. Well, these r vectors always, this r vector always goes from the center of a circular or spherical motion to the point that you care about. Yeah, right. So in this case, that circular motion is this, rotating around that fixed point. That's the center of the circular motion. And so r is the vector from this pin to B. So that's 0.200. And so the acceleration of B is equal to 0, 0, alpha 1, crossed with 0.200, and that is 0.2 alpha 1, 0. So that's the easier one because you have a fixed point there, so that you don't have to use relative motion. For member 2, we don't have a fixed point, so you always have to use relative motion. So the acceleration of B relative to the ground, according to member 2, is equal to the acceleration of B relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. And this is what our A2 represents. The acceleration of B relative to the center of mass is equal to alpha 2 cross a new r vector plus omega 2 cross quantity omega 2 cross r2. Like I said, these r vectors always go from the center of a circular motion to the point of interest. What's the center of our circular motion if we're calculating if we're calculating the acceleration of b relative to the center of mass of 2. Yeah, right. So this is a way to think of this is like we're calculating the acceleration of b pretending like the center of mass of 2 is fixed. So that's the center of our circular motion. Or maybe an easier way to think of it is whenever you're calculating the acceleration of some point b relative to another point, the center of your circular motion is the point that you're doing it relative to. So in an expression like this, center of mass of 2 is always going to be the center of the circular motion. So we just need a vector that goes from the center of the circular motion to the point we care about. So that's the circular motion we're talking about. And so what's R2? Well, you got to use sine cosine, but you get negative 0.07171717, negative 0.071710. Oh, this shouldn't be a 1. That's why that sounded weird to me. This should be a 0.
Why is that negative? Are you going from center to, or from that negative to the center?
No. 9! You should be going from the center of mass to that point. R is always from the center of the circular motion to the point of interest. Okay?
The point of interest is center of mass.
No, that's what we're assuming is fixed. So that's the center of our circular motion. The point we care about is we're trying to find the acceleration of b.
Is the R vector not negative 0.02535?
Yes, it is. Thank you. Because that distance is, I did it like that distance was 0.1, but the distance from the center of mass to this is only 0.05. So, all right, so the acceleration of b relative to the center of mass of 2 is equal to 0, 0, alpha 2 crossed with this new r vector plus body 2 has an angular acceleration. It's clockwise of 100, so this is 0, 0, negative 100, crossed with quantity 0, 0, negative 100, cross r. And so then the acceleration of b relative to the ground is equal to this expression plus a2. And now we set this equal to this. Kind of a mess. So set the acceleration of b according to the two members equal and you get that 0.2 alpha 1 is equal to, I'm just going to write it like this, acceleration of b relative to the center of mass of 2 plus a2. So this is what goes there. And then you just have this big expression that goes into your system of equations. All right, so like I said, you're going to want to be comfortable with this for the test next week. Anybody have any questions about this? Okay, the R vector goes from the center of a circular or spherical motion, but we've only been doing circular, to the point where you want to find the velocity or the acceleration. Okay. Anybody have any other questions about linkages before I go back to rotating coordinate systems? All right, so let's do this example. So you have an object that can rotate about this pin. And there's another object, another member that can rotate around the first one. We'll call that point P. This member is rotating in this direction with an angular velocity of 20 radians per second and an angular acceleration in the same direction of 10 radians per second squared. And this member is rotating about the pin connected to the wall at 10 radians per second squared and has an angular acceleration the other direction. I said squared here, but that's an angular velocity. So this is just 10 radians per second. This one's 15 radians per second squared. And each of these distances is 1 meter. Each of these members has a length of 1 meter. We couldn't do it because we had no way to specify the angular motion of this, if we call this member 1 and this member 2. Like, think of, if you imagine this thing going, so this one's rotating down while this one's rotating this way. It's a really complicated rotational, combination of rotations that's going on here. And we had no way to represent that. But now that we have a way to do calculations in coordinate systems that are rotating, we can fix the coordinate system to the object that's being ridden, and then do one circular motion calculation and then correct for the coordinate system rotating. So the problem is this complicated set of rotations. As an aside, we did do problems like this, if you remember, where you have one member rotating this way and another member rotating this way. So what's the difference between this and this?
The rotation.
Yeah, the difference is that the rotation of the member that's connected to the wall didn't affect the rotation axis of the second one. And so it was easy for us to represent rotations of the second member in this case. In this case, it's really hard. Okay? Yeah, that's one way to think of it. I mean, it's not just that they're in different planes of motion. It's that the plane of motion that this one's rotating in keeps changing because this one's rotating.
Right. Okay. It's the plane of motion is relative of member 2 is relative to the plane of motion of member 2.
Yes, that's right. Yep. So that's the idea of the horse/cowboy thing. You know, one of those planes of motion is being affected by, you know, the cowboy's plane of motion is affected by the horse. Okay, so we want to figure out the acceleration of p. Okay, so which of these members is the horse and which one's the cowboy? Which one's the horse? Yeah, one is the horse. The angular position of 2 doesn't have any effect on the plane of rotation of 1, right? So that's sort of the key thing to see. But the angular position of 1 does affect the plane of rotation of 2. Okay? And so this one's along for the ride. This one's controlling the action. And so we want to fix the coordinate system to the horse, to the one that's in control. And we're going to do it 2 ways because I think this is a good exercise. So if I call this pin A, the connection here B, we're going to do it first with a coordinate system rotating with body 1. With the origin fixed at A. And then we're going to do, this is the one that you want to do, and really, in a way, I'm doing this as 2 separate problems so you can see just so you can make the distinction so you know where to pick it right. This is the one where you want to pick it to make it simpler. But we are also capable of using a coordinate system rotating with body 1. But with the origin fixed at B. Okay, so the first one, coordinate system, origin, let's see, fixed at A. This is the easier one to think about. So the first thing we have to figure out is we know that this is a non-inertial coordinate system because it's on a body that's rotating. Is it only non-inertial because it's rotating, or is the origin also accelerating? This one, yes. Okay, so think about, so if it's fixed at A, as this thing rotates, that coordinate system's just doing this. Okay? So that origin isn't going anywhere. It's fixed to the wall. The only thing that's happening is those axes are changing orientation. So in this case, we don't have to worry about the origin accelerating. Okay, yeah, the origin isn't moving. In the second example, are we going to have to worry about that? So in that case, the origin is going to be fixed over here. And as this this arm rotates, the origin's going to be doing, that coordinate system's going to be doing that. So the origin is going to be accelerating and the axes are going to be changing orientation. And that's going to be a pain. Okay, so since the origin's not accelerating, what don't we have to use? What would we have to use if the origin was accelerating? Relative motion. So all we have to use is that crazy new equation. And so now what we have to do is, okay, so what we're going to use is we're going to use the acceleration of p is equal to the acceleration of p observed in the coordinate system plus the time derivative of the angular velocity of the coordinate system crossed with the position vector plus 2 times the angular velocity of the coordinate system crossed with the observed velocity vector of p. This position is of p2. Plus angular velocity of the coordinate system, cross quantity, angular velocity, cross position of p. Okay, so to use this, we need the acceleration of p that would be observed in this coordinate system. And we need the velocity of p that would be observed in this coordinate system. Well, we also need the position. And that position of p, the one that's observed in the coordinate system, is also the true position vector. So we don't have to specify observed or actual. Okay, so in order to calculate those observed velocity, observed acceleration, and the position vector, we can assume for now that that member 1 is fixed, okay? Because whatever member 1 is doing, the coordinate system that's watching the motion of p is also doing, okay? And so so according to that coordinate system, this coordinate system, how would you describe the motion of p? Like, is it a square wave? No. I mean, like, okay, I mean, it's a circular motion, but can you see how, so as this moves, and that arm moves, this still just keeps moving in circular motion. What?
So it goes up.
Well, I mean, it's just circular motion. Just imagine that this was fixed to the wall.
This
Okay.
is we're doing this in 2D, right?
Yeah.
So
Well, no, actually, we're doing it in 3D. Yeah.
Okay. So
I mean, this motion is in 2D, but it's in a different 2D than this motion. But just imagine, so if that coordinate system is a camera, what does it see this point P doing? It can't see anything else except this point P. And this camera just sees that point P moving in a circular motion. Okay? When it's in this position, it sees it like that. When it's in this position, it's doing this, but the camera is looking at it such that that circular motion looks just the same.
So this was just like a propeller. Just
Right.
launching it around.
Yeah. Okay. So, anybody have any other questions to help clarify that? Okay, so according to the coordinate system, the point P is just moving in circular motion. So the velocity of P that's observed is just equal to the angular velocity crossed with the r vector. The acceleration vector of P that's observed in the coordinate system is just the watermelon equation. And so we just need to think about what, if we imagine temporarily that member 1 is fixed to the wall, what's the angular acceleration vector of the circular motion of member 2? It's 10, and it is, so if our coordinate system, for this one our coordinate system is this, right? For the next part our coordinate system is going to be this. So according to this orange coordinate system, the angular acceleration is, use the right-hand rule, and it's in the negative x direction. And the angular velocity is in the same direction, negative x direction, but it has a magnitude of 20. Okay, so we have 0, no we don't, we have negative 20, 0, 0 for the angular velocity. And then the r vector goes from the center of the circular motion to the point of interest. So what's the r vector in this case? 0, negative 1, 0. So cross with 0, negative 1, 0. And so you get 0, 0, 20 meters per second. And then for the observed acceleration, that's 0, negative 10, 0, 0 is the angular acceleration. The r vector is the same. So 0, negative 1, 0. The angular velocity is negative 20, 0, 0. Crossed with negative 20, 0, 0. Cross 0, negative 1, 0. So that's 0, 0, 10, plus negative 20, 0, 0, crossed with 0, 0, 20. So that's plus 0, positive 400, 0. So the observed acceleration is 0, 400, 10. And then what's the position vector? That is the r vector. So remember, the r vector and the position vector are not the same. So the position vector is just, it goes all the way from the origin to here. So it's negative 1, negative 1, 0. That's in meters. That's not the same as the r vector. Now, the only other stuff we need to use this rotating coordinate system equation is we need an expression for the angular acceleration of the coordinate system and the angular velocity of the coordinate system. So what's the angular velocity vector of the coordinate system? In radians per second, yeah. So now the coordinate system isn't moving with member 2. The coordinate system's moving with member 1. So the coordinate system has an angular velocity of negative 10 radians per second in the z direction. You see that? So 0, 0, negative 10. And the angular acceleration of the coordinate system is positive 15 radians per second squared in the z direction. So now the acceleration of p, plug all this in, and it's the observed acceleration, 0, 410, plus the angular velocity of the coordinate system, the angular acceleration of the coordinate system, crossed with the position vector, plus 2 times the angular velocity of the coordinate system, crossed with the observed velocity vector, plus the angular velocity of the coordinate system, crossed with quantity angular velocity of the coordinate system, crossed with the position vector, negative 1, 0. So that's 0, 410. Plus 15, negative 15, 0, plus this one goes away because cross product of 2 parallel vectors is 0. Plus 0, 0, negative 10. Crossed with negative 10, positive 10, 0. So that's 15, negative 385, 10. Plus 100, 100, 0. So 115, negative 285, 10. Yeah. So I don't know. It's I think my best advice is you need to be systematic, approach it the same way every single time, and each time you do it, things that didn't make sense the last time are going to make sense. But it's going to just take a lot of practice, and that practice should be the same way every time. So next class, I'll do this same example with the coordinate system moved over to that other point, so the origin also has acceleration, and we'll see. Yep? Yes. So then this would be positive 485. Yeah. I have the answer right here. Okay, any other questions? Okay, that's it.